Hello? Can y'all hear me?
Yep.
All right. Hello, everybody. Thank you all for coming to my talk, Carrier Pigeon, where I will be diving into the world of decentralized communication with LoRa. All right, so before we jump head first into this, let me tell you a little about myself. My name is Leonardo. I just graduated from high school in July. I'm fascinated with embedded software and cybersecurity. Okay, so if you're anything like me, you worry about how secure your data is, and arguably more importantly, who might be viewing it or tampering with it. That worry is what inspired me to start working on this passion project, Carrier Pigeon. I will mention that the project is more of a proof of concept and learning experience for me and for you guys, as currently better alternatives do exist for consumer use. I also have a bunch of funky ideas I wanted to mess with in the future, which is kind of more of the reason why I created this project, because I wanted a good baseline, which I understood, so I could work on it later. We'll start by identifying some of my main concerns with instant messaging providers, and then we'll come up with a way to alleviate these concerns. All right, so that brings us to our main worries. When it comes to the current data protocols and providers, the first and arguably most important is there is a surprisingly large list of providers that do not keep messages and data encrypted when it is stored on their servers. One of the reasons for this brings us to our next reason, or our next concern rather, is message scanning. I don't know about you guys, but I'm not a huge fan of people who are not the intended recipient reading or having access to a message I send or data I upload. Many providers scan messages, whether it be for illegal activity, hate speech, or just general run-of-the-mill ad personalization. Either way, not something I'm interested in. Third and finally, although I could keep going on about this topic for a while, a common practice some companies use for when users decide to delete data is just tagging it as deleted, and they won't actually delete it until a later time. It's called soft deleting, and it's something I'm not too fond of. It means, essentially, you could send something, they keep it on their server, whether it be encrypted or unencrypted, and they hold it for a day or two, or maybe even a week, who knows? It's their choice, right? All of what I just mentioned is a threat to your privacy, and in my humble opinion, private conversation should stay private. Furthermore, this is why I started the project. All right, so that brings us to the idea. How can we solve this problem? Decentralized communication. What this means is it is not a central server holding your data, but it's peer-to-peer. So you have essentially relays that never get the plain text, and they never hold the data, it just goes through them and to the peer. That means no one can view the data or hold the data that is plain or plain text, it's just all encrypted end-to-end. To accomplish this, I decided on using the trusty ESP32 as a base, equipped with a LoRa module. Now, let me introduce you to the ESP32. If you aren't already familiar, ESP32 is a low-cost microcontroller. It's equipped with Wi-Fi and Bluetooth, and you can write firmware for it in a large amount of languages, as well as code blocks if you're not familiar with certain syntax. Due to the simplicity and the power of the device, the sky's truly the limit. You can make a variety of things with this. I've made some things in the past, I did a talk on one of them. It's got a lot of fun to mess with. Now, LoRa I'm relatively new to. It is a radio protocol that uses spread modulation, which is essentially modulating chirps, which are lower frequency, I guess, packets that are sent back and forth, and they're cyclic. So it's low power, wide area network is what LoRaWAN is. That is the kind of physical layer of LoRa. Using lower frequency chirps, it can actually transmit a little further than the standard radio and have lower power usage. So practically, open air, you can probably get 2 to 5 kilometers depending on your setup. However, this range can be extended with large antenna, optimal positioning, because obviously clear air means better transmission, so higher up, and of course relays to bounce back and forth. Just a side note, the world record for longest LoRa communication is 1,336 kilometers. Pretty far. Now for the fun part. I'm going to let you guys try it out, and I am going to need one volunteer who has a phone or a Wi-Fi connected device. All right? First come, first serve. There you go. Now you guys can see this little setup I brought. This is one of the ESP32s with a LoRa module and a screen on it. Now I brought one for me, one for my friend over here. What's your name?
Ben.
Ben, nice to meet you. So this one I drilled a little hole in there with a knife. I'm just going to connect the antenna on there. Batteries, I found them. There's a funny story behind these. You'll see in a second. I found them. So we'll power this one up. They are. You're smart, man. You know all about this stuff. Alright. I've got one set up and on. Take this one right here for myself. Plug this one straight into my computer. All right, there we go. There we go. Now we should be connected. If you're connected, you can try and send a message. Don't say anything raunchy. There you go. You go down here, say, hey man, how are you? Should come through. The basic premise of this is it's end-to-end encrypted. These devices act as dumb relays, which means they never actually encrypt anything. There is no plain text being sent ever. All the encryption is done on the device you're interacting from at the moment, which I will change in the future, but things are great. There was a 100 character limit. I tried to exceed it and it doesn't work too well. I thought about maybe breaking it up into separate chunks later, like multiple packets, maybe even images. Images would be cool. You could send maybe 20 packets and get like a 512 by 512 image across the yeah, that's the basic idea of it. Messaging.
So what's the network look like?
Network?
Yeah, so you have a Wi-Fi access point, you have a LoRa end. You have two LoRa pieces?
Yeah, you have a LoRa end for the peer 1 and peer 2, I guess, or sender recipient.
Right.
Initiator, responder, whichever way you want to put it. And it goes through WebSockets to transmit the encrypted message and other events, I guess, to the front end, which is JavaScript, and to the back end, which is the LoRa device frequency. WebSockets, async web server, and access point. And then LoRa is transmitted just as a number. It's relatively simple as far as the stack. How these off.
So what's the distance you guys should be able to communicate?
Theoretically, passed out the building.
Yeah.
Yeah. Those are the line settings, yeah. If I put a bigger one on it, it could go definitely further.
So what's the frequency that LoRa works on?
So from North America, we have a set broadband is 915 hertz. That's the only one we're allowed to use for LoRa. For Europe, it's different, and Asia as well. Let's see.
So is the encryption being done on the client device, on the web itself?
Yes. Yeah, it's being done on the client device. This is because I thought it would be a flaw by the way I have it set up, if it's sent to plain text over WebSockets or encoded text, that's a link in the chain that can be altered with, right? Someone could go in there, sniff your packet, and probably get the message it was sending if they were nearby you. For this, I do obviously have future advancements where that will never be a piece of the chain.
Is the encryption itself, like it's on clients, is that a pre-shared key, or are you doing, public-private key exchange?
That's the fun part, both.
Okay.
Both. All right. Does anyone have any questions for me before we get into how it works? I'll try and keep it relatively high level. Yes?
Do you have any concerns about just fundamental open design of computer networks generally?
For right now, it's not really scalable. Obviously, it's currently 2 device bound. I have future plans to maybe make hardware addresses that you can actually physically type in to target certain recipients. That would be more of a complex mesh, maybe using relays to forward a message kind of idea. But for now, it's just device to device.
Okay, and then do you have any concerns around like interception or jamming?
I mean, that's obviously a problem, but it's not very easily avoidable. If someone's jamming a frequency that is, I believe, a federal crime. Yeah, if they could jam the frequency, they'd have bigger fish to fry than just get rid of my message. But I would say for that, I do have a solution in mind that might be shown in future talk. It's interesting. I talked to my buddy up there about it. All right, so let's get into the tech stack briefly. It starts off here, the hardware and the software. Hardware has the firmware, which is USB async servers and WebSockets and LoRa. And then for the software, it's kind of broken off into the encryption, the, I guess, event protocol, and just the general JavaScript WebSocket stuff. So, like he said, recycled vape batteries is indeed what I used for these. I was walking out of work one night and I saw like 30 of them in the parking lot. And I was like, you know what, I'm gonna take these. So I took them, went home, tore a couple apart carefully. They can't explode. And I found out they actually almost perfectly match the required specifications for a lithium-ion battery for an ESP32. So I saved myself about 20 bucks in batteries, which is cool. I have a bunch more at home. I'd like to thank my buddy Nate for this idea. It wasn't mine. I took it from him. You can see my wonderful, beautiful soldering job over there. The kit came with no flux, and I was in a time crunch, so it was definitely fun. All right, now for the fun part, the actual code, at least for me. I'll try and keep it relatively high level, not too complex. However, if you do want to check it out, it is all publicly available on my GitHub. So let's get started with the firmware. First thing we do is we initialize our ESP async server, and we start the little file system, which is what we use to store the JavaScript library, and we use the library for the crypto. It's not mine, I'm not that smart. But we use the library for the crypto, and we have a couple of JavaScript files we load on as routes. So when you hit the index, which is the default page for just the default route, 192.168.1, then you are forwarded all the CSS, HTML, and libraries required. Then we have the LoRa. So there are defined configs that you set up when you use LoRa. There are some that you can change, some that you definitely should not. Spread factor, like I said, LoRa works with spread modulation, which means your signals are not always the same. They're using a multiplier or a factor. Lower spread factor means shorter messages, or I mean longer message times, but more accurate messages over a longer range. However, if you want something a little faster, you're going to lose that accuracy, you're going to lose that integrity, I guess, but it'll be super quick. So I chose something a little in the middle, like 7, a little more leaning towards speed. Then you obviously can't change the RF frequency. That is a set allowance you are allowed in North America. If you try and use a different one, you will get in trouble. After defining the config variables, we just listen for the LoRa events, which are done through the radio library. We have transmission received, we have reception received, And it basically calls the event when you're done sending a message and receiving a message. You can see the snippets in there if you guys are interested. And yes, you do have to take the string buffers and put them into message buffers, which is a little annoying, but it works. Of course, we use WebSockets for live updates on the chat server, as well as for sending messages back and forth between the devices. It's kind of just a normal event handler we have there. It runs through. The only different thing the only thing that separates it from a regular WebSocket event handler is it only allows one device at a time on the WebSockets. That is because the way I designed it, I didn't want 5 people joining your particular LoRa device if they found the password and messing up the procedure. In the future, maybe I could have multiple clients at once, but that's not now. Now we'll briefly look at the front end side of Carrier Pigeon, which is where the crypto is done and a lot of the traffic handling. Yeah, for this version of Carrier Pigeon, all the crypto is done, like I said, on the front end, and the LoRa kind of just acts as a dumb relay. In the future, I have plans to make it all on the device. That way there is no other link in the chain. So the first thing we have is the contact between the two devices. What it is a hi message. It'll send hi back and forth until they reach each other and they both act, which means they have recognized they're both there. After that, it starts doing the key exchange for Diffie-Hellman, and it starts doing the public key crossover, and then eventually it will enter ready mode, and then instead of a hi, it will send a heartbeat every 5 seconds to ensure that the computer is still connected. In order to use most forms of encryption to their full potential, you have to first exchange a key and derive a shared secret. Now, I first generate a salt key pair. That's the library we're using for crypto. Salt, it's a JavaScript ported library. And I generate a key pair for secret box, which is our form of encryption. Now it'll create a private and a public key. They're both mathematically tied together, but they're very different. Right? We share the public keys via Diffie-Hellman, which is, you see the diagram up there. I'm not going to get too in-depth into it. It's a little difficult to wrap your head around, but essentially, you share 2 values. One side sends one, the other side sends one. You mix them with the values that you keep, and if done right, you should receive one shared secret that is the same but never explicitly said over the network. At the start of each session, we also create session nonces, which is a number used once. We send this nonce with the public key. That's just to keep everything in one packet. I could do it in 2 to confuse the threat actor, but I just did it in 1. During the key exchange, and we take both the session nonces and create a salt, which we'll use later in encryption. Carrier Pigeon uses these message nonces as well. So not only does it generate a session nonce at the beginning of every session, but a message nonce with every single encrypted message. Now for authentication and integrity. This is a big part of messaging. You can't just receive something and confirm, oh yeah, that's definitely from the person I expect it to be. If you don't have the right protocol set up, people can set up like a, what do they call that? Like a relay attack, I suppose, where they take something, a replay attack, that's the one, where they take a message you sent or someone else sent and they hold it, send it at a separate time, or they take the packet and send it. Now, this can be fixed to a degree with authentication. I have here a PSK, which is a pre-shared key. It is a value you and your friend make before communication ever starts. Usually a 32-byte value, or in my case it is. And the shared secrets, the PSK, and the salt are all combined together to make, well, with the HMAC, which is, we'll get into that in a second, to create basically a session key. Think of this like the master key, say. It's the one that really matters. Everything else is a piece of this puzzle. Your session key is your end-all key. Now, an HMAC is a hash-based message authentication code. So it basically takes a bunch of values you pass it, puts it into one big math algorithm, which I did not write, and spits out your session key or whatever key you expect. So what that looks like for encryption is we have two main functions. One, it takes the session key that you just generated, which, if done correctly, should be the same on both devices. And it puts it into Salt Secret Box, which is a Salsa 20 Poly 1305 kind of crossover encryption. Encryption is performed with the session key, as we saw earlier, and it's derived from Diffie-Hellman's shared secret, the salt, from the two session nonces, and of course the pre-shared key. Inside of the encrypt message function, we see the message nonce being generated, the secret box using the key we pass to it to encrypt the plain text. And when we call encrypt message, we give it the plain text message, and it returns back an encrypted message and a message nonce. These are then sent through WebSocket and then through LoRa. So by the time any transmission is made, it is already fully encrypted. That way there is no real way to see the plain text unless someone is on your computer. Now receiving is relatively similar. You just receive that encrypted package, essentially, that encrypted packet, and you put the nonce into secret box, you put the encrypted text in, and you pass your session key, which, yet again, should be the same on both devices. Now, this is kind of a simplified explanation, a little in depth, but if you want to check out the code in its entirety, it is all publicly available on my GitHub. Now, you may be wondering, where do we go from here? What advancements can we make? And I want to ask you guys the same thing. What kind of improvements do you guys think I should make to this software?
Forward secret?
Huh?
Forward secrecy?
It does have a little bit of forward secrecy there. Yep.
Are you reusing the same session key?
No, the session key is generated with each session differently.
Okay, how long is the life cycle of that?
That is a good question. So it is per session, so however long a session lasts. When a user disconnects, a new session key is created for both parties. So
Could you not just generate a new key for every message and then have?
you could. It would be a little heavier on the device, but it's definitely possible. I did look into that. I just opted for a little bit more client focus because that way messages would take significantly longer and use more resources to send. But it is definitely an idea if you wanted a little bit more encryption, I guess. Yep.
Right now, could you connect multiple client devices to a single peer?
You shouldn't be able to now. It has a check for the Wi-Fi network, which it has a max, I guess, connectees to 1. And WebSockets also has a fallback just in case someone does happen to slip in. It only allows one person to be connected to the WebSocket at a time, so even if they were connected, would not route their traffic.
Could you possibly allow that as a future thing?
Multi-client?
I'm thinking like a central, let's say disaster, a central command post that has one peer, but multiple clients connecting to that peer.
Yeah, so that would be more of a relay design. You could do that, or you could also, you could also have like a central point where, like you said, disaster relief, they could all connect to 1. That could be hosted. It would be hard to get a area network wide enough for a whole region to do
Well,
disaster
I'm
relief.
thinking like, you've got the command tent.
Yeah.
And you've got 3 staff members in that tent connected to the peer, but then you've got frontline workers out 1 or 2 kilometers away. from
Yep.
The range of LoRa. They might be a single client per peer or multiple client per peer if it's a team.
Oh, so you're saying kind of like a group chat kind of thing?
Yeah.
Yeah, that is very possible. Yeah, it's been done before.
And possibly having it set up as a mesh.
Yeah.
So if party A is too far away.
Like
from
relays, I see what you mean, yeah. That is also possible. So look into Meshtastic if you haven't already. They do similar stuff. Their main idea is actually nodes, relays, and meshes, hence the name. And it is really interesting stuff to think about because, like you said, if the range is just too far from one person, it could bounce that message off the other person. So it would be like a multitasking kind of thing.
I was at the Army's hackathon year, and one of the teams did use LoRa for communicating on front lines with, their, what is it, Cloud Pack.
Really?
Their tactical software that's just on an Android phone, they have strapped to themselves and they
Yeah.
can do their commands and drills, whatever.
That's really interesting.
But they're using LoRa as that relay to
Yeah.
get from, the front line, maybe to a,
More secure
a lab
location,
or
yeah.
bank that has a maybe satellite relay that
Mm.
can take it back to.
That's the cool part about it, right? You can transmit a message with these tiny devices, make it a couple kilometers, and then that can take it somewhere else, right? If it's in a safer location, you can send that up satellite, pass it down the chain, wherever you want. That's the cool part about it.
If the
Anyone else?
if the receiving device isn't in range, what, does anything happen? Like, can it, if it comes back into range, will it pick it up, or is it?
Unfortunately, at the moment, the packet just gets lost. I guess what I should be doing is acking the message as well. So when a message gets received, send an ack back, therefore I can tell when the packet is dropped and then relay it when it's connected again. That would be the smart thing.
There's
An improvement, true. Yep.
And then with the relaying your 5 seconds, are you gonna be able to average that to account for the hops?
Usually the hops don't take that long, it's within milliseconds, but I guess if you're doing super long range, like maybe 5 relays, 10 relays, then that might be something you would put into like an algorithm where it would say, okay, depending on how many relays we think this is going to be or how far we think this is going to be, how long should we wait for the heartbeat back, right? Yeah.
I was thinking, do you have a mobile application in mind?
I don't think I do I don't at the moment, no. But I was thinking about making a portable application, is what it's called, I believe. And I looked into it, but it would have been easier if I went that route, because you can do portable applications for both iOS, Android, and computers, but I decided to go the web page route with HTTP instead of using like a portable application with HTTPS and web crypto. I just went the separate library route because I thought it would be more usable, I guess. Because my idea with this was, you're on the front lines, right? You have an old device. Or say you're in the Middle East and you don't have access to newer technology. Well, you can still use, it's a web page, right? It's a web page with everything preloaded on it. HTML, CSS, it's on every single device for the most part. So all you'd have to do is hit the web page and you'd be able to communicate. Whereas older technology might not be able to work so well with apps. Yep.
Do you have a guide to like self-hosting?
I do have a guide up on how to do that on my GitHub, yes.
Okay. So like having like your own server?
Yep. Okay. All right, we'll continue. Here's a couple ideas I had. I have 3 that I came up with while working on this project. Didn't quite have enough time to do them for this presentation though. First one was, why even have an access point? Why even have that link that can be attacked, right? Like an attack vector. So, here's my beautiful illustration. It's not anyone else's property. And my idea is, what if I put a bigger screen on one of these and a keyboard, then I don't need that access point. It can go straight through the device, no Wi-Fi, only LoRa. And encryption's done on the device, it's more than powerful enough. That is a future advancement. Maybe even add solar, right? Say you're in the middle of nowhere and you need some sort of communication, you can charge it with solar, send a message wherever you are, right? And could work, depending if anyone's listening, right? Second idea, briefly talked about this with my friend as well. There are interesting methods of encryption that I was looking at. It would be more secure than the protocol I already have. Now, the one I used is already pretty forward. It has authentication, integrity. It's pretty high level encryption. It's not easy to decrypt or cut into, but there are literally unbreakable encryptions, such as one-time pad, which is a little iffy on if it's good for communication, maybe single use, but the idea of it is essentially there's a code that is good for one message. And after that, you'll have to refresh that code. So it would have to be kind of pre-shared, but it could work and be essentially unbreakable. So that is something I would look into in the future. And finally, third and finally, the most obvious is if you want to extend range, bigger antenna, better position, and relays are the obvious options, but I have come up with some more unconventional ways to extend range that I would really like to experiment with in the future. Little hint, you gotta go high up in the air. You might see it in a future talk I'm doing, but I don't want to go too much detail just now because it's a rough concept. So conclusion, technology like this is fascinating. However, obviously at this time, my project, Carrier Pigeon, is not scalable for the masses. I decided to show it off as a project of mine to inspire other like-minded individuals to experiment with new protocols, new devices, and new ideas. It's one thing to use pre-existing libraries, but it's important to understand how these things work, why they work, and how we can make them better. Meshtastic is an amazing option if you are looking for something similar. They have an application on most phones. They're pretty widely used, more widely adopted than any other LoRa protocol. And they're pretty good. They have DMs, group chats, all of that. But if you are a little less on the schizophrenic side or paranoid side, then you might want to just stick with Signal. Signal is definitely the best mobile option right now. All right. That unfortunately brings us to the end. I would like to thank you all for coming to my talk, and a special thanks to the BSides board for making this all happen. If you're interested in staying in touch, you can come up and grab a card. I have a lot. I am looking for an entry-level job or internship. If anyone's interested. That being said, does anyone have any questions? Yep.
With it high up, would you be using anything that's publicly available to deal with the time differences?
Time differences.
You start running into problems with it high up.
Yeah, it wouldn't be like crazy high. I was thinking more local region high up, not like
Not
lower
satellite.
over.
Okay.
That is somewhere I wouldn't
So
want to go
satellite
mention.
time does have a different time than us.
Yes, it would. But that is something far in the future for me. I wouldn't be able to launch a satellite until at least university.
You probably get it on like those experiment trips.
They do those at some universities. It's like where NASA runs them, I think. They let you launch like CubeSats and do testing for.
Yeah.
Yeah.
Are you thinking of strapping to a drone?
You got the right idea, man. Yeah, that's the idea. Yeah.
If it's drone and those things. So I'm a physicist, actually.
Yeah.
So like, would you be testing also with the range, the like integrity as well as any interference with like, stuff that comes from the sun or
It would be a lot of testing because once you throw something into the real world, as I'm sure you're aware of physics, right? There is a lot of factors. Like in a room, there's a lot less factors than when you put it out in the sky on top of the drone.
Yeah.
And I had more ideas with the routing as well. It would be not just a standard position for the drone, but moving around, right?
Yeah.
A moving relay per se. Now, once you start putting movements, like different altitudes, you have weather conditions, you have all these different aspects where you need to kind of take them into account when writing radio protocols. Yeah.
Yeah, real pigeons.
Yeah. Anyone else? All right, I think that's it. Thank you all.